Hello, everyone. Welcome to the last session of our summer series. Here I have uh, with me Venki today. If you have been following our summer series, then you know that we both are product engineers, structural engineers working with GSD idea, and we are also there on the help desk. Now, without much of delay, we are moving on to the questions. So, just moving to our first question, which most of which we get asked in the help desk most of the time. So, what if my section shape is not listed in IDEA StatiCa's library? That is, if you are taking from template or if you are starting from scratch, you are unable to create a section on your own. So, how can I still model and analyze it? So that's a question. Um, we have already discussed about it in detail in one of our workshops, the workshop that the GST idea conducted. So it goes like this. I'm just going to demonstrate it a bit. So for that, I'm going to start the application. Now I've opened IDEA StatiCa application, and in here, I'm going to start with the connection application. I have my application here. So I'm just going to select a random design or a random connection, and I'm going to create the selected design. Now, if I want to make this section a very different section, which is not available in the cross sections that's there directly. That is, if I have to change the session, then as I always mention, you have to start from the new option, that is the plus option, and never to go with the edit option. I'm going with the plus option, and then under welded composed, here are the sections that needs no additional change. You can just select from it and then have it. So if it's a T section that you're looking for, or if it's a um, double channel section that you're looking for, then you can directly select from this. But if not, then this is the option. Select on this, and then you can customize your shape. Click on the edit option, and there will be a general cross section editor that pops up. So if I want to make a um, very plain or a very cruciform kind of a section, then I can go with this one. I can select a plate with the shape, with the shape that I want, and also the material that I would like to proceed with. I can just click on OK. And in similar way, I'm just going to create one more cross section. So this, I've defined one, and I'm just going to define one more, the same plate. I'm just going with the same width, and I can see that there's a red uh, grade mark, which basically means that it is superimposed. Now I'm just going to rotate it to 90 degree, any one plate to 90 degrees, so that I can get my desired shape. And I could, all I have to do is to just click on OK, and again on OK, and I'll be able to get the shape that I wanted. If I'm just going back with this one, and I can give it this. So this is how exactly you create a section, desired section. Now, if you find any of these warnings, just check what are the warnings exactly. Now, this, since I've selected a parametric template, the template has got certain upper and lower bounds, which is why the warning and the parameters has been displayed. Now, if I want to eliminate this, I can just click on it and then I can explore this. And I could see that I have my cross section right over here. So that's how exactly we create our desired cross section. I hope that is clear. And let's move with the next question that we have. Uh, what are the most common reasons IDEA static analysis fails or stops before producing the results? Okay, so this is a very general question. I would say that this is a very vast question. So many times we get screenshots saying that okay, this is what happened. The analysis is not proceeding. It stops at zero and it doesn't reach 100%. So please note that this is a very vast question, and this can't be described in um, um, uh, one or two recommendations. So for that, we need a proper understanding of the model and how it is modeled. So mostly this is related to modeling. Something have gone wrong in the modeling, and 80% of it is related to the modeling, and 20% of it is related probably to the material, the direction, the orientation, or if the weld hasn't been placed properly. So it all brings down to one thing, that is the model. And we need the IdeaCon file to actually understand what has gone wrong, where has it gone wrong. But for now, we are going to tell you um, the common troubleshoots that you can also check from your end if any of these goes wrong. Now, so the first one is that you might have taken it from a template where the stop at limit strain is already activated. And if that is activated, then the load wouldn't be transferred, or the 100% load wouldn't be applied. The analysis or the iteration stops right when any of the elements, that is plate, bolt, or weld, any of these fails. Now it need not be the plate that it fails all the time, or it need not be the bolt, or any of the connection component. If when it starts to fail, it stops. So for that, what you can do is you can go to the code setup. That is the project setting. Now the code setup was in the earlier versions. For now it is the project setting, right over here. And you can go to the analysis, and you can just uncheck the stop at limit strain and save it, and then proceed with analysis. So if your analysis stops somewhere in the mid, that is, it's not 0% that I'm talking about, somewhere in the mid, that is 50, 60, 40, etc., then check this one first. And then if it is toggled on, then you can turn off and then proceed with analysis to know that what is the level of failure that the bolts, as in this case, would expect when 100% of the load is applied. Now the next problem, or this next possibility, is that it could be a very complex joint. So when I say complex joint, it's not the straight joint that I mean, but a joint with multiple direction members in multiple directions, and also multiple operations. So in those cases, mostly this happens in circular sections or hollow sections. Now, so the reason for this is that the iteration capacity might not be enough. The current iteration capacity might not be enough to actually keep the analysis running. So what we have to do is to just increase the iteration capacity, or increase the number of iterations. So by default, the iteration is kept as 25 and divergent iteration count is 3. And what you can do is you can bring it to the number of analysis iteration to 50, and then divergent iteration count to 5, and then save it, and then run the analysis again. Then check if that works well. If it works well, then it's the reason is that it's a very complex joint and it's too complex for the software to understand or keep the iteration running. Now the third error, this I would say is a very common error and very it's there from the beginning of the analysis. So when the bearing member, especially when the bearing member is a hollow section member, and when the GMNI is active, the iteration fails in between. So because uh, if the section, if the bearing member, that is a hollow section, is overloaded, then iteration fails in between. Why? Because it's an FEA analysis. So in this case, we can disable the GMNA, that is geometrical and material nonlinearity. So we can disable that and then run the analysis. So IDEA StatiCa gives you a warning that GMNA is recommended, but when it is a bearing member and when the analysis stops in between, then this is the current workflow. This is the only current correction to that failure. Now, the next one is usually when you have, for example, this type, the clamp type connection. So you can see that the bolts are connected to different plates, but there is no connection. There is no direct connection with the top flange, the top flange of the beam. So, uh, so in here there would be very small prying shear forces that can lead to singularity error. So to counteract these prying forces, we need to provide something called as the utility weld. Now, what exactly is a utility weld? It's just it's a normal weld itself, but just provided to make the software understand that there is a slight contact somewhere and it's not sliding anywhere. And um, uh, uh, so the best part is that you do not have to provide the utility weld continuously. You can make it partial. Now it's not a different operation, it's not a separate operation as utility weld. It would come under the same operation weld, but you make it to a utility weld when you change the type. As you can see in the presentation, you need to change the type as continuous to partial, and you can provide a very small offset just for the software to get that there is a contact between it, and then run the analysis. So that's that would be the primary step. And later, when it comes to the result interpretation, you can ignore the results for that weld. You can ignore the results completely for the utility weld. So next time when you're working on a clamp connection and the analysis stops at zero, then this is the method. And yes, now coming to the meter cut option in IDEA StatiCa, especially when it comes to hollow section members, then um, the analysis stops at 0% as well. Now it's more on the it's more based on the orientation or the it's the 1D element orientation for, especially for butt weld. It doesn't happen every time, but meter weld and circular hollow cross section, we would definitely opt for the butt weld. And if we opt for the butt weld, then this is the failure that we get. So the reason is that it's due to the misaligned angles. If you can see it in the enlarged figure right over here, there would be some disruption within the model, and it wouldn't be located as shown in here. So to make it right, what we can do is we can provide a bit of an alpha rotation. That is, you can rotate it a bit to adjust, self adjust, and then provide correct butt. Now uh, the value, the magnitude is not the important factor here. It's not exactly for every model 2.3. It could differ. from connection to connection, it could differ. So you can change the alpha rotation value and then try running the analysis again. Now, yes, um, I don't know if you have noticed this, but these days this is the most common source of the error. I'm not limiting this to connection application, but I'd like to take it this also to the concrete application, be it 2D or especially not much in 3D, but when it comes to the connection and 2D, I've noticed this quite so often, that the physical properties of the materials are marked as null, as are given a null value. So um, you might have defined it earlier, and while you define it, there might have been a duplicate of the same, which was created using the null values of the physical properties. Now this could be the reason when you're recalling a grade from another code or another environment, then this usually appears. And also, this could be also due to the import option, the wrong import that has happened. So due to many reasons, the steel or the materials, be it the steel material or be it the bolt material grade, uh, that would provide zero value. And now in connection application, it is the physical properties that usually takes the null value. But uh, when it comes to the 2D detail, it's also the physical properties, but mostly the modulus of elasticity, that's automatically taken as null value. But that's something that you get a warning as well, that the elastic modulus has exceeded the limit. So when you see that particular warning in your 2D detail application, then go straight to the materials and check the elastic modulus of elasticity, and also saw in here the materials. And um, the next and the most common one, as I've mentioned, everything can be can be just shortened to one single warning, which is the wrong modeling. When something is not connected properly, when something is not welded properly, when anything is not connected, or when the members are not connected to each other, then it gives a singularity warning. But at that time, if that is a reason for the zero analysis, then you would get a warning as singularity. Then if you get a warning as singularity, then all you have to do is to just go to the check, as mentioned in the presentation. You go to the check and you will find the reason, or you will find the exact cause of the singularity there, because you will find the plate is moved to somewhere, so you will get the name of the plate as well, so that you can just come back and then rearrange it. Okay, so that were the common causes of singularities or the 0% analysis. But as I've mentioned, it depends from connection to connection. So if so, these are the primary troubleshooting methods that you can try out from your end. If that doesn't help, then check your model. I would also suggest you to check one more thing. Check the member orientation. So just like how we corrected the alpha value in here, alpha rotation value in here, uh, certain models, when we import it from any third party software, the alpha beta gamma values might have a slight change. It might not be always zero. It could be minus or plus or minus 1.1 or 2 mms um, tilted, which gives no space for the butt weld, especially when you're butt welding. And at that time also the singularity might happen, right? And to the next question. So this is using the slotted bolt holes. Does the software account for possible bolt movement within the slot, or is it always based on centered positioning? Okay, so these are two questions. Um, does it account for the possible bolt movement? Uh, uh, so I should say that yes, the software does take into account that the bolt can move in the direction of the slot. That's there. But it also means it doesn't let any force transfer happen in that direction, which kind of simulates how the bolt can slide a bit inside the slot. Now, the second question, is it always positioned centrally? Um, yes, actually, the actual reason is that the bolt looks center and is positioned centrally, but the software assumes it doesn't resist load in that direction. Also, there needs to be at least one plate with the standard hole, that is the central standard hole. Otherwise, the connection wouldn't be stable, and the analysis also wouldn't work. Now, for those who doesn't know that there is a feature of slotted bolt hole in um IDEA StatiCa, I'm just giving you a slight representation of the same. I'm taking the same model. I'm just going to switch it back to a normal section, and I'm just trying to connect it via fin plate. Just trying to import the operation of a fin plate. Now, once you have the fin plate in here, all you have to do is to just click on the plate. You can either right click on it and go to the editor, or you can directly go from here to the editor. And these are the options for you to provide the slot, either as this or vertically as well. And you can also control the length of the hole, the slotted. And now this is the slot on the fin plate. Now, if you have to provide the same slot on the web, the member web, that is also possible. Now, how is that possible? Just go to the BG1, and this is the web plate web, and you can just give the same slots in here. But please note that the both the connected plates should not have the slots. At least one should have the normal slotted, the standard slot. I'm switching the fin plate back to the standard one, and I've kept the member slot as uh, the slotted one, and I can apply it, and then I'm pressing it on OK. Now, going back in here, I can see that this is the slotted hole. Now, this is a very new update in IDEA Statica 25. Earlier, the slot was only limited to the fin plate, only the plate or the manufacturing operation. But right now, we do have the provision to provide it on the flange, I mean, on the web of the member as well, to any connected plate. But it's just that the drawback or the limitation as of now is that at least one plate should be kept as the standard one. And on to the next question. If a global model includes diaphragm or rigid floor effects, how should these be represented in IDEA Statica when modeling the joint? Okay. Uh, so this comes under, again, we have discussed this on our workshop, one of our workshops, and we thoroughly discussed how this affects and how this changes all the connection. Now, I have a very short answer to this one, that there is something called as a lateral torsion restraint, LTR, in IDEA Statica application, both in connection application and in member application, which would completely simulate the same effect of the rigid floors. That is, it prevents the torsional buckling, and that this is where you can provide that from. So if you go to the operations, and this is the option to do so, lateral torsional restraint, and you can just click on it, So you can define the plate where you want the lateral torsion restraint to be, and if you want it to be on a full plate length, or you can define how with the offset that where exactly you want it in the connection. And also you can define the type, if you want it as a continuous one or if you need a discrete one with joints. And also regarding as the LTR has two restraints, one is for the torsional one, that is which is applied around the plate's local x-axis, and there is lateral restraint applied in the local y-axis of the plate. Now you can define it if you need it as a rigid one, stiff one, or a free one, or you can even set a defined stiffness for that one. So this is exactly the option for it. That is LTR. That would be the shortest answer for this question. Yes, these are just some extensions of the same lateral torsion restrained option. That is, you can, as I've mentioned, you can define the offset if you want it to be continuous or discrete, and also you can set the stiffness of the same. Now, this is one typical example with the with a provided stiffness, manual stiffness, and also a discrete with an offset. Now, the fifth question is that I finished modeling in a connection under Eurocode. My client now wants AISC checks. What's the fastest way to make this switch? So, okay, the question is more about switching the code, which is as of now not directly possible in IDEA StatiCa, but there is a workaround. I could say that it's a very short workaround right now, because after a few times, or a few iteration of practice, you will find it the shortest. So for that, I can start with the connection library in here, which I think would be much better. So you all know what exactly is the connection library, right? So this is the IDEA StatiCa connection library. I'm just going to click on try connection library. uh, I'm going to define two members, one I section and then one horizontal, very small one. And then I'm going to search, and I get n number of results from here. And I'm just going to take one random result. I can choose this, and I'm going to download it now, and I can open it. I've just got my connection opened right over here. Now I can see that this is in Eurocode, and there are two members like this. So if I want to recreate the same section in AISC code, all I have to do is to just publish this connection. I'm just going to publish it as a personal one. I'm going to publish it. And now I'm going to start a new one in AISC code. I have it here. I'm going to change the design code. I'm just keeping the subcodes as it is. I'm just going to take a random one. I'm going to create the design. And now I am going to uncheck these operations, and I'm also going to explode the same. Since I've taken a parametric template, and we're just going to explode it, and I'm going to click on the propose option, and towards the end of it, or somewhere here, I can find the published one, and I'm just going to recall the same property, And I can see that it is the original source is this, and I'm going to convert it to AISE. And if I need to make the necessary material assembly conversion here, I can do that, but I can do it later as well. So I'm just clicking on OK, and I have my connection in here, which was earlier in the Eurocode and now in the AISC code. So the direct switching, as I mentioned, is not possible. Uh, but this is a workaround that you can try. But for that, all you have to do is to just define the members. The members are to be defined, but the rest of the operation you can just bring in just like that. Completely fair. Now, if you are a Eurocode user, there is an application, design converter application that IDEA StatiCa has released. You may check that out as well, but it's now limited to Eurocode. But um, hope to hope to get a better extended version very soon. Now, this would be the yes. So this is the easiest method as of now you can do for converting any connection to any other code. Now, with that, I am passing the presenter to Venki. So, Venki, over to you. Can you hear me?
Yes, Rose, I can hear you. Let me share my screen. Mm, okay, Rose, I hope you can see my screen, correct? Okay, great, thanks. So let me continue with the questions. The sixth question. It was in AISC design, do the global buckling limits depend on the steel grade? Uh, how would things change for a higher grade materials like S460 or what comes like 620, so on, etc. So on what basis the buckling limits are calculated? So we already know once we run the buckling analysis, the outputs are the buckling mode shapes. Uh, use the buckling mode shapes, we can classify whether it's a global buckling or a local buckling. And the second output is the critical buckling factors, like you can see the factors 5.5 and so on. These are all critical buckling factors, so we will compare these factors to the limits. So we are talking about those limits on what basis the AISC limits are derived, because as per Eurocode it is very clear that the limits for the elastic analysis is 10 and for the plastic analysis is 15 for the global buckling mode. But this was specified in the code itself, but as per AISC, we do not have any code specifications for that. So how the limits are arrived in IDEA StatiCa? So that was the question. So I will show you this slide in which in IDEA StatiCa website articles, you can find the global buckling factor limits for some grades like 36 KSI, 50 KSI, like 12.7 and 9.16. But let's just understand how it was calculated, so that if you are using some material which was not there in the shown limits or shown grade, you can calculate yourself the buckling limit. So the main reference for this calculation is solely based on uh, J chapter 46 clause, or even the chapter E of AISC 360 represents the same, which is the nominal compressive capacity is equals to yield strength into gross area of the component multiplied with safety factor gives you the design compressive capacity. But to get this yield capacity, the condition was LC by R is less than or equals to 25. What happens if this condition is not met? Uh, there is the second equation, B equation for this, but this equation will consider the reduced yield capacity. So IDEA StatiCa does not go to the secondary equation. It will consider the full yield capacity. So the equation for that is LC by R is less than or equals to 25. So this is the equation which is considered for this calculation. And we know the Euler equation Fe equals to pi square E by LC by R square. And we'll substitute all the constants like E for steel, and LC by R is 25. So we'll substitute 25, we'll get the Fe value, and alpha CR is equals to ratio of Fe to the yield strength. So, for example, if you want to calculate for 36 KSI, here it was considered as Fe by 36. So 458 by 36, it's 12.7. So if you have your custom grade like S355, S460, so on, etc. So you can substitute this E value along with LC by R. This remains a constant because we are deriving it based on LC by R equation less than or equals to 25. So based on this, you can actually calculate your own buckling limits for any material grade you use. So, and the next question, in IDEA StatiCa stiffness analysis, how does the software decide whether a joint is pinned, semi-rigid, or fixed? What are those limits based on? So, yes, basic classification happens based on moment rotation curve as given in the ASC code or Eurocode, any code. And we will have some limits for the pinned, and we will have some limits for the rigid, and we will the application, the solution will calculate the moment rotation curve based on input moment, and the moment rotation curve will be plotted so that if the curve falls in between the limit of the pinned limit and the rigid limit, then it is classified as semi-rigid. And if it is less than this pinned limit, then it is classified as pinned. And if it is more than rigid, it is rigid connection. So the question was like, how? What is the basis for this? So for this, again, if you refer back to the code, uh, code has suggested already like the classification will be based on moment rotation curve, and we'll have two stiffness, initial stiffness and second stiffness, as shown here, plotted in tangent to the moment rotation curve. And in addition to this, code also specified the limitations for the pinned limit as well as the rigid limit. You can see here the equations KSL by EI greater than or equals to 20. Then we can classify this particular connection as fully restrained. And if KSL by EI is less than or equals to 2, then it is classified to be simple. So what IDEA StatiCa does is like it just took these equations, and since we are interested in the stiffness, we sent everything else to the other side. So Ks for the fixed fully restrained will become 20 EI by L, and for the pinned it will become Ks is equals to 2 EI by L. And if you see the graph, you can see the pinned limit is 2 EI by L and fixed limit is 20 EI by L. And the same is represented in IDEA StatiCa as well. You can see once you analyze, and if you go to rotational stiffness, you can see the fixed restraint limit value and the pinned limit value. Both of these equations are automated way to calculate that manual calculation, which is like this is 20 EI by L and this is 2 EI by L, and the same is plotted in the graph. This line corresponds to this value 846, and this represents 2 A by L, and this yellow line represents the fully restrained limit value, which corresponds to 20 EI by L. So these are just calculated automatically based on what's specified in the code, and it's nothing new. So that's all the content we want to discuss in this presentation. So some of the resources and tech support before uh, ending the session. As you know, you can reach out to IDEA StatiCa website. In the support center, you will have all theoretical backgrounds about CBFM and also CSFM, and you can go through it in detail. And also a lot of tutorials were there which will give you IDEA StatiCa native files as well. You can just download them and uh, check its understand it. And also the webinars on various content was already prepared for you. If you're interested in knowing about anything in detail, you can watch the webinars. All are there in the support center. And if you're stuck any point, anytime, and Unfortunately, because of the time constraints, if you couldn't resolve some questions of yours, then please do write to us at support@gsd.ae, and we will give you a satisfactory explanation or solution. And we do offer some of the advanced trainings. All these are hands-on trainings. If you're interested, please do contact us for the steel connection design, member design, and as well as the concrete discontinuities. You can reach out to us at support@gsd.id, and we can discuss further on that. And finally, please scan the QR code and give us your feedback for the session so that we can make the session better. And this will be the final session for the summer series, which we have. And one more point I want to share with you, like just give me a minute. Okay, if you're modeling any connection, I just want to highlight uh, the ease of if we use the propose and publish options, you can understand how easy it is to uh, uh, model the connection very quickly. For that, a small demonstration, 1.5 minute or 2 minutes, you can just see this. In the propose option, you can go to the selection when there is no template for the overall connections. In the selection, you can select the geometries in which you want to propose your particular connection first, so that one end of the geometry you can select and propose any template which is there in the database. And you can go to the second direction, and similarly you can select the geometry and propose the template. So the second template, and the third one. So as of now, you can like propose multiple templates, not just one template. So you can divide your connection into multiple segments and apply various templates. You can combine multiple templates to form your connection. In general, this connection modeling might take you maybe 25 minutes to 30 minutes, but using this method, we just finished in 2 minutes. So you can take full advantage of this. And that's all. A few here and there cuts are there, and we can just adjust this. So if you are if you are spending a lot of time on your connections, then try using the smart way, which is using the propose and publish options, which will give you a flexible solution. And that's all for my presentation. Considering this the last presentation, Rose, do you have anything to add?
Hi, Venki. Yes, there is nothing technical from my side to add right now. All I have to say is that let's get in touch with each other on the support, and feel free to ask all your queries. But I'd like to extend a very big thank you to all of the IDEA StatiCa users in Gulf who have helped us make this event a very big success. So, thank you so much. Yes, that would be all from my side. Thank you.